Hello everyone, welcome back to our channel. This is the question series for the questions that you can expect in the GATE DA exam. So today what we are going to cover are two very easy topics that are very scoring as well. So we'll talk about K cross validation or K full cross validation. I might be using these terms interchangeably, so please don't get confused. And the other one is leave one out cross validation. So let's get started with our first question. Okay, so the question says, suppose we want to compute 10-fold cross-validation error on 100 training examples. Okay, so they are saying they want to compute the 10-fold cross-validation and on 100 training examples. So when they say 10-fold cross-validation, that means that K is equals to 10. So in K-fold cross-validation, here K is equals to 10. And when they are saying that they have 100 training examples, we usually use n to denote the number of training examples or samples. So that is equals to 100. Fine. Now they are saying that we need to compute the error n1 times, and the cross validation error is the average of the average of the errors. So in what happens in cross validation is you basically divide. Let's go to a blank page and see what is K cross validation first. Yeah. K cross validation. Okay. So usually in this scenario, what you are given is n is equal to number of samples in your training. Number samples in training. So when you want to do K cross validation, there could be multiple reasons. One is you want to check the generalization error of your model, or you could do hyperparameter tuning. So hyperparameter tuning is so model has a lot of configurable parameters. For example, batch size, or say how many number of layers you want to use in your neural networks. These are some of the examples. So you might want to fix that using this particular approach, which is K cross validation or K full cross validation. So what you do is, so you actually divide your, so you have n number of samples, right? You create K subsets of it. So this is my n, right? And I create K subsets of this. Fine. So every subset is of size n by K, right? This is also n by K. This is also n by K. And what you do is, you train K models. K models are trained. And evaluated. So sometimes what happens is you don't have test data and you don't know the performance metrics of your model that you are going to train. So use K cross validation to divide your training data into multiple train and validation or test sets, and then compute the error on those individual test sets and average them out using K fold cross validation, and then you get an idea that okay, this could be my training or could be my test error or the test time error. So so now K models are trained. So what you have is, let me create this in a better way. Yeah. So you have 1, 2, 3 K minus 1 folds, right? So when you are training model 1, okay, so what we do is we take the K minus 1 folds for training. and only one fold for testing. Correct? Right? For model 2, 1, 2, 3, k minus 1, k minus 2, k, right? So for model 2, what you'll do is you will take one fold for testing, and you go like this in round robin fashion, and these ones you will use for training. This is model 2, and like that you will train k models. So kth model, when you are training kth model, how will you train? So you have 1, 2, 3, k minus 1, k minus 2, k minus 1 and k, right? So what you'll do is you will use, so you can see the pattern here. So whenever I am training model 1, I am using, so this is not, this is an exceptional case. When I am training model 2, I am using the k minus 1th fold for testing, right? So here if I have to say that I am training kth model, so I will use this fold for testing, and you will use this. Let me do this in a different color actually, so that it's easier for you to understand. Yeah, so we'll do k. Actually, let me add k here. So you will add these all in training. So let's do a small example to understand this better. Suppose I have 90 samples, okay, and I want to do 3 cross validation. So what will I do is, these are my 90 samples, let's assume. So I'll divide them into 3 folds, right? So number of folds is equals to 3. Size of a fold is equals to n by k, where n is equals to 90 and k is equals to 3. So that means it's 100, sorry, this is 90 not able to erase this, okay. Yeah, so this is 90 by 3, which is 30, okay. So basically I'll have 30 samples here, 30 samples here, 30 samples here and 30 samples here. So if I have an index for those samples, suppose, so they are starting from here, so 1 to 30 here, 31 to 60 here, 61 to 90 here, correct? I'll just write it. So sample 1 to 30 here, 31 to 60 here and 61 to 90 here, right? Now every time I'll train a model. I'll train how many models? We'll train k number of models, right? K models are trained and evaluated. So we'll go back. So we have to train model 1, model 2, model 2 and model 3. Now tell me, which fold, how are we going to use them for training and testing? Okay, so let's say this is, so it had 30 samples here, 30 samples here, 30 samples here, right? 1 to 30 here, 31 to 60 here and 61 to 90 samples here, right? So total samples we have is 90. Out of 1 to 30 samples are in fold 1, which is fold 1. Second fold is of size 30 as well, and the number of samples we have in it is 30, and they are from 31th sample to 60th sample. This is our fold 2, and this is 61. The number of samples in the third fold is also 30, and the samples are from index 61 to 90. Okay, so what will we use in training? So we will use k-1 folds, right? K-1 folds for training, which means we will use 1 and second fold for training. Actually, you can use any of the fold. You have to make all the combinations. So to just be in an order, we do like this, that we'll start from 1 and 2 and keep it in testing. Then we'll move forward in a window. We'll use 2 and 3, keep 1 in testing, right? So 1 and 2 fold for training, right? Training k-1. And testing, what will you do? Testing mein you will use third fold, correct? Similarly, here what you will do is training, you can use 2 and second and third fold, and testing you will use first fold. Then in model 3, what you will do is you will use first and third fold for training, and for testing you will use the second fold. So if you can see, this is very clear. So we are training model k times, right? And we have k folds. So for every model, one of the folds, and only one of the folds is in the testing, and such that all the folds come in testing at least once. Okay, all the folds come in testing at least once, right? And we have k models, so, and we have k folds. So what does that mean? Let's calculate the number of samples for training, right? So we know that for every model we use k-1 folds, and we have total of n by k samples in one fold, right? We can go back and see that every fold is of size n by k, right? So when we are using k-1 folds, right, and number of samples for testing is equals to, we just use one fold, and one fold has n by k values in it or samples in it, so that's the number of samples for testing. Okay, having done this, let's come back to the question and see if we can answer it now. So let me read the question again. So they are saying that suppose we want to compute 10k cross validation, so k is 10, and we have 100 training samples, so our n is 100. We need to compute the error n1 times. So they are saying ki we will have to compute the error n1 times. So what is n1? And the cross validation error is the average of the errors. So in cross validation, once we have trained all the models and we have computed the error on each of the models, we just take the average of them and say that okay, this is the error for the whole data. Now to compute each error, we need to build a model with the data size of n2. So they are saying n2 is equals to training data size, right? So every model is being trained with this. So what is the data size for training is n2, and then test the model on the data size of n3. So n3 is our testing data size. Okay, so now we have done all of these three, so let's try to answer them here. Okay, so so we said that k models will be trained, right? So n1 was equals to number of times error was computed, which is also equal to number of times models are trained, which is equals to k, right? So let's go back to our solution. So we know that this is equals to n1 is equals to k is equals to 10, right? Now let's go to n2. It's saying it's a training data size. Okay, so we discussed that in training we use k minus 1 folds, right? So we use k minus 1 folds. So k minus 1 folds, right? So k minus 1 folds, so total samples in training is equals to k minus 1 into size of a fold, and we know that now that the size of the fold is n by k. So this is n by k. So let's plug in the values. What was the k? K was 10. So 10 minus 1. What was n? N was 100 and k was 10, right? So we have 9 into 100 divided by 10, which is equals to 90, correct? So coming back to the question, n2 is equals to number of training samples and we computed it to be 90, correct? Now let's go to the computation of number of training sample, number of samples for testing. So number of samples for testing is 1 fold and n by k. So I will do it here. So for testing, okay, so for testing we have 1 fold into n by k samples, that is equals to 1 into 100 by 10, which is equals to 10 samples. Okay, so we have 10 samples, so our n3 is equals to 10. So let's see which of the option is true. So they are saying n1 is 10, correct, n2 is 90, correct, and n3 is 10 is equals to this. So this first one is our solution. Okay, let's see the answer. So A is our solution. Let's move on to the next question. So the question says, consider a data set with 1000 samples. So n is equals to 1000. You need to do the 5-fold cross validation for model evaluation. So k is equals to 5. So if you use 80% of the data for training in each fold, how many samples will be used for testing in each fold? Okay, so this line is kind of redundant here because just with these two information we should be able to calculate the values. Okay, so what they are asking is for, they are saying you use 80% of the data for training in each fold. So let's try this out ourselves. So we know that we use k minus 1 folds for training and every fold is of size n by k. So we use so here we are doing 5 folds, so 5 minus 1 folds for training, and 1000 examples we have, and cross validation is for 5. So we have 4 into 1000 divided by 5, right? So this will be 200 and this will come out to be 800, right? So they are saying that 80% of data, 80% of n is for training, and we also find that 80% of data as if is for training, and we also found out that 800 samples are used for training. So what is the number of samples we are using for testing? So for testing we know that we use 1 fold, and for one model we use just 1 fold, and 1 fold has one fold has n by k samples, so which is equals to 1000 by 5, right, which is equals to 200, correct? So coming back to the question, so we computed that for samples used for testing is equals to just one fold, and one fold has n by k samples, n is 1000 here and k is 5, so which is coming to be 1000 divided by 5, we just did on the previous slide, so this is equals to 200, okay? So 200 is our answer. Let's see what's the answer. The solution is C, correct. Okay, next let's move on to the next question. So they are saying, suppose we are performing leave one out validation and 10-fold cross validation on a data set of size 100,000 to pick between 4 different values of single hyperparameter. Okay, so what they are saying is, so they are saying that this is leave one out cross validation, or LOOCV is being done, and also they are saying, so leave one out cross validation, and they are saying we also want to do 10-fold cross validation. Okay, so there is M1, the method 1, and then there is M2, which is 10-fold cross validation. Okay, so they are saying we have 2 methods. Now they are saying that the data set is of size 100,000. So what is n? N we know is 100,000. Okay, and they want to pick, and we to pick between 4 different values of a single hyperparameter. Okay, so I think we talked in the previous slide. In one of the slides we talked that we can use cross validation for hyperparameter tuning. So what is hyperparameter tuning? So hyperparameter tuning is nothing but, suppose that you have 4 parameters and you want to see which parameter, what value of this parameter. So suppose that you have 1 parameter and you have 4 values for it. So you have hyperparameter tuning. Okay, so what is hyperparameter tuning? Hyperparameter tuning is nothing but, for a parameter you have multiple values, right? You have some x values. So these can be x1, x2, blah blah blah, xn, right? Now for every parameter, for every value we will train models or do cross validation and compute error. Okay, so value with least error, with least cross validation error is chosen. Okay, so it's nothing that for every parameter you will be doing 1 round of cross validation. So let's come back to here and see that they're saying they have 4 different values for the single hyperparameter. Okay, so basically they're saying that you have to do x, or 4 times you have to do cross validation, right? How many times greater is the number of models that need to be trained for let me just remove this line. Yeah, I think it's got highlighted. How many times greater is the number of models that need to be trained for leave one out cross validation versus 10-fold cross validation. Okay, so they are asking, right? So they are asking very simple question. They are asking models trained for leave one out cross validation, how many times they are greater than models trained for 10-fold 10k CV. Okay, so they have already given that the number of models that are trained for leave one out cross validation, it's actually leave one out cross validation, is greater than the number of models that are trained for 10k cross validation, and they are just asking how many times greater. Okay, so how many times greater, if we have to compute, how we'll do that? We'll calculate how many times we'll have to train the model for leave one out cross validation or LOOCV, and then we have to calculate how many times we have to train the model for 10 cross validation. So let's get started. So we know how to do 10-fold cross validation, so let's do that first. So here n is equals to 100,000, right? And you want to do 10-fold validation, 10 cross validation, so 10 folds. So k is basically, so k is equals to 10. So this is not required. So here k is equals to 10. So we know from the previous questions that models will be trained k times, which is equals to 10, right? So for one iteration or for one parameter, we have to train the models 10 times, right? But we have four values of hyperparameter, right? So we have to train that 4 into 10 times. For every parameter, we'll do the cross validation. So there are 4 parameters. So for every parameter, if you are doing cross validation for 4 parameters, how many times will you do cross validation? You will do it 4 times, right? So 4 times you will do cross validation. One cross validation is taking 10 models. So 4 cross validations will take 40 models, correct? Now let's come to leave one out cross validation. Okay, before that, let's just see what is leave one out cross validation is. So leave one out cross validation. Okay, so what is leave one out cross validation? So it's a special case of k cross validation, right, where k is equals to something. Okay, so let me first put the idea behind and we'll find out what this k is. So in leave it out cross validation, what happens is, suppose you have n samples. Okay, so you have 1 2 3 3 dot 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 dot, you have n samples, right? So I'll say n minus 1 and n samples. Okay, so in leave one out cross validation, you just take one sample out. So you will basically test on this and you will do training on this. That's right. Okay, so this is model 1. In model 2, what we'll do is, model 2, you will 1 2, these are your samples and not folds here. So these are your samples. You have n minus 1, n minus n folds, right? So you will do testing, or you will just remove the sample 2 and you will do, so these you will use for training. Okay, training. So basically now your test set has only one sample and rest of the samples are in your training. Okay, so this is leave one out cross validation. So you're just leaving one sample out. So you're leaving one sample out for testing. Okay, now let's back to our question that what is the K. So we know that testing has just K samples, right? Sorry, testing has just n by K samples, right? So in testing we have only n by K samples, which is equals to 1-fold, correct, from the previous knowledge. So here we are saying that n by K is equals to 1, right? Because I just told you that we use just one sample for the testing. So n by K is equals to 1, which means that K is equals to n. Okay, so here it's a special case of K cross validation where K is equals to, or let me write in a different color, K is equals to n. Okay, so in every model you will just keep one sample out. One sample out for testing, and rest of the samples will be used for training. Okay, let's come back to this. So here K is equals to n, right? So when K is equals to n, number of models for one leave one out cross validation is equals to n, which is equals to 100,000, right? And we have 4 values of parameter or the hyperparameter, and so how many times we have to do it? 4 into 100,000, right? So these many times we have to do the cross validation, or these many times we have to do the model training. Now the question is asking how many times greater is the number of models that need to be trained for leave one out validation. Okay, so it's asking how many times greater. So how many times greater, how will we compute? So we know that the number of models trained for leave one out cross validation are definitely greater than models trained for 10 cross validation, but why number? But with what number? So we have these two values. So we have 400,000. So this is actually equal to, we have 400,000 models that we are training for leave one out cross validation, and we have 40 models that we are training for 10 cross validation, 10k CV, right? So if I have to cut this, so it's just 10,000. So it's just 10,000 times greater. Okay, so the answer is 10,000 times greater. Okay, let's see what the answer is. Yeah, so the answer is 10,000. Fine. Let's move on to the next question. So this is asking what is the cross validation not used for. Okay, so it's an MCQ question, and it can be a multiple choice. So multiple statements can be also correct. So let's look at every one of them and figure out that which one is not the statement for which cross validation is used. So to evaluate the performance of machine learning model on unseen data, so this is correct. We actually want to evaluate the performance of machine learning model on the unseen data, and that's why we keep those test folds separate. Test folds are for this purpose only. So this is correct. Then, so this is actually a point and not a cross. Yeah. So to select model hyperparameter, we just talked that we can use cross validation for model hyperparameter. So we know that cross validation is actually used for models hyperparameter tuning to determine the generalization of a machine learning model. So generalization is nothing but how good it is performing on the test data or on the unseen data. So yes, it is used for the generalization of a machine learning model as well. And to train multiple machine learning models on different data set. Well, this is not correct, right? So we don't actually train multiple models. So this is not correct. So to train multiple machine learning models, we actually just train one model. So suppose we are using neural network, we'll just train all the models that we train, all the models that we train in cross validation CV are the same models, So it is not like that for one model or one model that you're training, you will use neural network or KNN in one, or say some other model in one. It's not like that. So you don't train multiple models, you just train one type of model and you don't train multiple type of models. So this particular solution is not, this particular statement is not correct. So this is actually the answer, because they are asking what is the cross validation not used for. It's not used for training multiple machine learning models. When they are saying multiple machine learning models, they mean different type of machine learning models. That's not true. We just train one type of machine learning models for all the models that we train in the cross validation. Okay, so let's come to the solution. So this question was taken from the Washington University. Actually, all my questions have been taken from some of the universities midterm exams. So you can actually refer the links and see the solutions yourself. Okay, so they are also saying that D is not correct, which means the answer is correct, but these we don't do cross validation for the statement that is being said in the D. So, and the explanation that they are giving is the answer to train multiple ML models on different data set is a correct one. Correct one as in we don't do cross validation for this. We could argue that CV trains the same machine learning model on different partitions of the same data set, but not multiple ML models on the different data set. So when we say multiple models, it means multiple type of models. Multiple type of models which we don't train. We just train the same set type of model every time for the cross validation model. Okay, let's come to the next question. Okay, this is one of my favorite questions. This is a very interesting question. Let's solve this. So this read what the question says. Consider a nearest neighbor classifier. Okay, so they are saying you to consider a nearest neighbor classifier. So when they say nearest neighbor classifier and they haven't mentioned a number like 2 neighbor classifier, 3 neighbor classifier, it's 1 neighbor classifier that chooses the label for the test point to be the label of its nearest neighboring training example. Okay, so if it was not clear from here that it's one nearest neighbor, they have made it clear that for the test point to be the label of its nearest neighboring training example. Okay, so the nearest neighboring example in the training set will be used to label the test point. So now they are asking what is the leave one out cross validation error for the data in the following figure. So if they have given this data and they are saying if you are using one nearest neighbor, what will be the leave one out cross validation error. Okay, so they are testing two for concepts here. So one is nearest neighbor and the other one is leave one out cross validation error. So these kind of questions you can definitely expect from GATE as they test multiple topics. They test multiple topics at the same time, and this question has also been picked up from the Washington University. You can refer the link here. Okay, so to deal with this, let's first label the data, or I'll just name the data points so it's easy for us to do this. So I have 5 data points A, B, C, D, E. Fine. So let's solve this question. So we have I'll just see once. Yeah, so you have data points like this. Okay, right, you have some data points like this. Now okay, let's say that you don't have, or let me go back. Let's start from data point A. Okay, I will keep this in test. Okay, and I will keep rest of them in training. So when we are training a nearest neighbor classifier, you actually don't learn any parameters. Your training data is your model. Okay, so whenever the data point comes in the training data, you will look for the nearest sample or the nearest neighbor, and according to that, you will mark the the test point. Okay, so now A point is in my test. Fine. So when A point is in my test, and these are my training samples. These all are my training samples. So this is all my training data, right? This is my training data. Training data. Okay. So when A point comes in, I will find his nearest neighbor. So if you can look at the data, you will find that B is the nearest neighbor. So A's nearest neighbor is B. So here we are writing nearest neighbors. So A ka nearest neighbor is B, right? So A is now, so because we have, and B is positive in the training data. So how will we label A? We will label A as positive. Okay. So A will be labeled positive. So let me erase this actually. Yeah. So A's neighbor will be is B, right? So A is labeled positive, right? So it's labeled positive. Okay. So A is being labeled positive. So but the actual label of A is negative, right? So A is not labeled correctly. Fine. Now let's come at B as the test point. Right. So now let's leave out B. Okay. Now this is in test. Okay. So now this is in test. So and let's forget this also, because this is not the label. We will only use true label of A in training set. So now B is in test set, correct? So B is in test set, and rest of the samples are in training set. So how will we label B? So we'll find the nearest sample of B. So nearest sample of B, if you can see, is A, right? So B's neighbor is A, right? And B is labeled as negative. Okay. So B will mark as negative, but true label of B is positive. So B is also not labeled correctly. Okay. So it will contribute to our error. Okay. Okay. Let's remove B as well. Now let's say we'll take the C sample. I'll remove this. Okay. Now we'll take the sample C. Right. C. So C's neighbor is, nearest neighbor, if you can see from the picture, it's B, right? And so C will be labeled according to B. The label of true label of B is positive. So C will be labeled positive, right? And the true label of C is also positive. So C is classified correctly. Correct? Now let's go to sample D. Okay. So sample D, or the test point D, when it's in test point, rest other points are in, so this is test. Okay. Rest other points are in training. Okay. So we'll find the nearest neighbor of D. So nearest neighbor of D's neighbor will be, D's neighbor will be E. Okay. And E is labeled negatively. So D will be also negatively labeled. So D's true label is also negative. So D is classified correctly. Now let's talk about E. So E, let's leave out E and construct the classifier with the rest of the samples. Now E comes in, we'll find the nearest neighbor of E. So nearest neighbor of E is D. D is labeled negatively in the training set. So E will also be labeled as negative, right? And the true label of E is also negative. So E will be labeled correctly, right? So out of 5 samples, 2, A and B we are not able to label correctly. Rest 3 of them we are able to classify correctly. So for every iteration we created one model, one nearest neighbor model, and we kept one of the data points outside and in the test set, and we evaluated on that. So the total error we have, so out of 5 samples I am not able to classify 2. So error is equals to, I am not able to classify 2 correctly, so I will just take the average of all the errors, so which is equals to 2 by 5, right? So okay, so this is not needed. Yeah, so model 1 error was 1 equals to 1. A is misclassified, right? Let's go back. A is not classified correctly. Model 2 error is equals to 1. Error is equals to 1 again. B is misclassified. Classified. Model 3 has error 0. Error 0 because C is classified correctly, right? So C is correctly classified, right? Model 4 error is equals to 0 because D is correctly classified, right? So if you go back, D was correctly classified, and also E is correctly classified. So model 5. So model 5 error is also 0. E is correctly classified. So we saw how we use leave one out cross validation, right? And also how we use the nearest neighbor. So this is leave one out cross validation. Now it's CV plus 1NN, one nearest neighbor, right? So now we'll take the average. We talked about this previously. So CV error is equals to 1 plus 1 plus 0 plus 0 plus, because we have 5 models, divided by 5. So this is equals to 2 by 5, right? So let's see what's the answer. So the answer is 2 by 5. On to the next question. So what are they saying is, leave one out cross validation is a special case of k-fold cross validation where, so this we have talked about previously, that leave one out cross validation is a special case of k-fold cross validation where k is equals to n, right? So the training set contains all but one sample and the remaining sample is used for testing. So this is correct, right? We saw that we have n-1 samples in the training set and there's just one sample in the test set. Okay, the training set contains only one sample. No, this is not correct, right? Training set comprises of n-1 samples. The training set contains exactly one sample from each class. This is also not correct. The training sample can contain any n-1 samples from the data set. So this is not correct. This is also not correct. The training set contains one sample from each fold and the remaining folds are used for testing. No, that is also not correct. So there are actually n folds and each fold has just one sample and we'll take n-1 folds, right? So this is also not correct. So the correct answer is A. So this question was also taken from the Washington University. You can refer to the link to the question. Okay, let's come to the final question of this video. So this is similar to what we did previously, and it should be very simple for you to solve. Okay, so let's start. So for the following data set, circle the classifier which has larger leave one out cross validation error. Okay, so it's saying that out of these two, that is one nearest neighbor, 1NN is actually one nearest neighbor, and this is actually 3 nearest neighbor. So basically whenever you are using your data set, whenever you are using your whenever you are labeling your test sample, here you will look at just one nearest sample, and here you will look at 3 nearest samples in your training data to give the label to that test sample. Okay, with this understanding, let's solve this question. I will draw this here. So this is like this, right? So this is your data, correct? So let's start with one nearest neighbor. Okay, so like previously we did, we will keep one sample out at a time and rest will be our training samples. Okay, then we will, for this sample, then the sample that was left out, we'll try to find the nearest neighbor, and whatever is the label for the nearest sample, we'll just label it that way. Okay, so for this calculation purpose, let me name these data points so it's easy for us to do that. A, B, C, D, E, F, G, H, I and J. Okay, let's do this together. Suppose, so I will so this is my test sample. Okay, test sample. Okay, so my test sample is, say, for example, say D. Okay, so rest of the other things are in my training. Okay, so I will find the nearest neighbor. So nearest neighbor of D. Okay, so you can look at this data and you will see that, suppose that this one is 1 and this is also 1. In the original figure maybe this is more clear. So this, suppose this is 1, distance 1, and this is also 1, right? So we know that the distance on the diagonal will be 1 under root 1 square plus 1 square by Pythagoras theorem, right? So it will be under root 2. Under root 2 is greater than 1 point something. So this is greater, right? And then this will be half. This point will be at the half. So this will be under root 2 by 2. Okay. So this point will be the nearest point for this, the ones that are on the corner. Okay. So for D sample, the nearest point will be C. Nearest neighbor of D is equals to C, right? So D is labeled according to C. So D will be labeled as positive, right? So D is being labeled as positive, correct? Which is incorrect, right? So D is actually positive. The true label of D is positive, but it's being labeled negative. Actually, sorry. Oh, this is incorrect. So the nearest neighbor of D is C. The label of C is negative. So D will actually be labeled negative. Okay. So D is actually incorrectly classified. Okay. Let's do for E. Right. Actually, let me do it on the next slide. Yeah. Okay. So my test sample is, say, E. Okay. So nearest neighbor of E is C again. So E will be labeled negative, right? So this is also incorrectly labeled because the true label of, so this is the true label. So though we are predicting it to be negative, true label is positive, so misclassified. Fine. Okay. So D is also misclassified and E is also misclassified, right? Similar, also not classified correctly. Let's do for A. Okay. So again with the same logic, nearest neighbor will be C. So A is labeled negative, which is incorrect, right? So misclassified. Right? Okay. Now we know D is misclassified, E is misclassified, and A is also misclassified, right? Now let's do for B. Again with the same logic, nearest neighbor is C. B is labeled negative, so misclassified, right? The true label of B is positive, but because it's the training set, C is the nearest point to B, so it's being labeled as negative, so this is also misclassified. Okay, so B is also misclassified. Now let's talk about C. Okay, so for C, they are actually all the labels A, B, and D and E are nearest neighbors. So whenever this happens, so what we do is, when we have multiple neighbors which are near to one data point and we are doing one nearest neighbor, we take the max vote. Okay, so A, B, C, D nearest neighbor, right? So, and all of them are positive, so C will be negative, labeled as positive if it's in the test set. This will also be misclassified, right? So C is also misclassified, correct? Now let's come to the so this is also misclassified, this is also misclassified. Let's come to the right side of the data set. So I'll just show you that for F, right? So nearest neighbor, like we did in the previous case on the left hand side, nearest neighbor is H. Okay, nearest neighbor is H, so F will be labeled as negative. This is correctly classified. Right? So this is correctly classified. Now let's talk about G. So G is also nearest to, so the nearest label to H is also, nearest sample to G is also H. So, and then label of H is negative. So G will also be labeled negative, which is correctly classified. Then again, so basically G is correctly classified. Let's talk about I. I data point is the nearest neighbor to the I data point is H, which is negatively labeled. So I will also be labeled negative, which is also the true label of the I. So it will be classified correctly. Now for the J data point, with the same argument, H is the nearest neighbor in the training set when J is not part of the training set, and it will be labeled according to H, which is a negatively labeled data set. So J will also be negatively labeled, and the true label of J is also negative. So this is correctly classified. Now talking about H, as we did for C, all the four labels are positive. All the four data points are its nearest neighbors, and all of them are negative. So if we do a max vote, H will be negative and it will be correctly classified. Okay. So let's talk about all of these samples: A, B, C, D, E, F, G, H, I, J, right? So A is not correctly classified, B is also not correctly classified, C is also not correctly classified, D is also not correctly classified, E is not also classified correctly, right? But F, G, H and I are corrected, H, I and J are classified correctly. So the total we saw that A is not correctly classified, B is also not correctly classified, C is not correctly classified, D is also not correctly classified, and E is also not correctly classified. While F, G, H, I and J data points are correctly classified in the leave one out cross validation, right? So because they are correctly classified, okay, so we saw that A is not correctly classified, B, C, D and E are also not correctly classified, while F, G, H, I and J are correctly classified. So out of 10 data points, 5 are not correctly classified, right? So error is equals to 5 by 10, right? So in leave one out cross validation, we take the, so error we have 1 here, 1 here, 1 here, 1 here, 1 here, 0 here, 0 here, 0 here, 0 here, 0 here. We'll add them up. Sum of 1 plus 1 plus 1 plus 1 plus 1 plus 0 plus 0 plus 0 plus 0 plus 0, right? And we'll take the average, right? Now let's talk about the 3NN classifier. Okay, so we are going to look at the 3NN classifier. Actually, let me just use a new slide here. Let me draw the data set again. So we have positive, positive, negative, positive, positive and all negatives here, right? So this is my data set. So in 3NN, what we'll do is, rather than looking at just one nearest neighbor, now we are going to look at 3 nearest neighbors and use the max vote for those 3 nearest neighbor to decide the label of the test sample. Okay, so sorry, I'll just go back. I'll just replicate this many times. So we are going to do 3 nearest neighbor classifier here, right? Okay, so let's again label these points. Let's name them A, B, C, D, E, F, G, H, I and J. Okay, so let's talk about A first. So nearest neighbor, 3 nearest neighbors of A will be, so you can see this distance is 1, this distance is root 2 by 2 and this distance is 1 again. Okay, so 3 nearest neighbors are B, C and D. Okay, the label of B is positive, C is negative and D is positive. So if we take a max vote, so we will get a positive label. Okay, so A is labeled positive. Okay, so this is correct. So this is correctly classified. Okay, okay. Now let's do for B. Okay, so 3 nearest neighbors of B are, so A is a distance 1, so A, D is a distance of root 2, so it will not be, C is a distance of root 2 by 2 and E is a distance of 1. So 3 nearest neighbors are A, C and E. Now label of A is positive in the training set, label of C is negative in the training set and label of E is positive in the training set. So we'll take a max vote. So when we are taking the max vote, so B will be labeled positive. So this is correct. So B is also correctly classified, right? Similarly, D and E are also correctly classified, right? So A is correctly classified, B is correctly classified, C is classified and D is classified correctly. Now let's come to C. 3 nearest neighbors are of C. Okay, so you can see that actually A, B, D and E all are nearest neighbors of D and E. So whenever you have more than 3 nearest neighbors, when the classifier is given as 3 nearest neighbors, but you are getting 4, you can actually take average or max vote from that the other neighbors. So here we'll consider 4 neighbors of C. So all the labels for these neighbors are positive, so C will be labeled positive. Right? So because C is labeled positive, this is misclassified. So can you start seeing the difference? So in one NN, all these 5 data points were not classified correctly, but here, because we are using 3 NN, we are able to classify 4 of the data points, and here only C is not getting classified correctly, right? Now let's look at F, right? So for F, nearest neighbors are 3 nearest neighbors are G, H and I. So and all of them are negative, so this will be labeled as negative, which is correct, right? Similarly, G, 3 nearest neighbors are H, F and J, which all are negative, so this will be negative, correct. Let's talk about I and J first. 3 NN neighbors are for I are F, H and J. All 3 of them are negative, so it will also be labeled negative, which is correct. The 3 neighbors of J are I, H and G, which are also correctly labeled, so this will be labeled correctly. Okay, let's talk about H. So H is at equidistance with F, G, I and J. So whenever this kind of a thing happens, right, maybe I didn't elaborate this in the previous setting. So whenever you are doing like K cross validation, K NN, but you have more samples which are nearest to them, sometimes they will give you like what needs to be done when you have more samples qualifying to become the neighbors. Otherwise, you can take the max vote of all the 4. Okay, so we'll take max vote of all the 4. So this is negative, 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 and this will be a negatively labeled data. So this is all; these are all are classified correctly. Okay. So now let's see A, B, C, D, E, F, G, H, I, J, K. K is not there, right? So let's go back and see that we saw that A, B, this is 3NN, yeah. So in 3NN we saw that A was classified correctly, B was classified correctly, C and D were classified correctly, but E was not classified correctly, right? So C was misclassified, and all F, G, H, I, J were classified correctly, right? So A is classified correctly. So if I have to write the error, A is classified correctly, so error is 0. B was classified correctly, so the error is 0. C was not classified correctly, so error was 1. D was classified correctly, so error is 0. E was classified correctly, so error is 0. F is classified correctly, so error is 0. G is classified correctly, so error is 0. And H is classified correctly, so error is 0. I is classified correctly, so error is 0. And J is also classified correctly, so error is 0. So the total error is 1 by 10, right? Now let's go back to the question and see what they were asking us. They were asking circle the classifier which has larger leave one out cross validation error. Okay, so we found out that NN had 5 by 10 and nearest 3 NN had error 1 by 10. So 1 NN has largest Okay, so what's the error? So the solution is 1nn. Since 1nn CV error is coming out to be 5/10, we also calculate the same, and C3nn, the CV error is 1/10, right? So 1nn is the answer. So that's all, guys, for today. Thank you for being so patient with the series. Hope you were able to understand the solutions of the problem that I posed. We'll see you next time. Happy learning.